In this video, we are going to see the relation between the autocorrelation function and the power spectral density. So the autocorrelation function and the power spectral density together form a Fourier transform pair, which is also known as a Wiener-Kincher relation. So what is autocorrelation function? It tells us a measure of similarity between the signal and the shifted version of the signal, and the power spectral density tells us about the power contained in the signal at different frequencies. So this is a general formula of the autocorrelation function, that is expectation of x of t1 into x of t2, and it is said to be WSS if Rxx of t comma t plus tau is equal to Rxx of tau. That is, it depends on the difference between the time but not on the time shift. So let's go into the proof. So we are going to prove that they together form a Fourier transform pair. For that, we are finding a function xt of t that is equal to x of t when t lies between minus t to t and 0 otherwise. So the Fourier transform, the general formula of the Fourier transform, so we are applying the Fourier transform for xt of t. So we get this. Now from the Poiseuille's equation, we also know the relation, that is x square of t dt is equal to 1 by 2 pi into integral minus infinity to infinity xt of j omega whole square d omega. So in order to find the average power, we need to just divide the equation with 2t and we need to change the limit to infinity and take the expectation of this. So we are doing that on both the sides. This will be equal to nothing but the average power. So we are doing the same even on the RHS side, that is even here we are doing the same, that is dividing the 2t limit t tending to infinity and taking the expectation. So this full thing will be equal to Sxx of omega, which is nothing but the power spectral density. So now we are solving this. We have already seen what is xt of j omega. There is nothing but integral minus t to t xt of t e power minus j omega t dt. So since we are having here whole square, we are writing this as expectation of xt of j omega into x conjugate of j omega. So opening everything, we get two integrals. Since we have already defined here xt of t is equal to x of t when it lies between minus t to t. So since we are having a whole square, one will be t1, one will be t2, x of t1, x of t2. Now afterwards, by just rearranging the terms and taking the j omega minus j omega common, we get this equation, and we have already know that expectation of x of t1 into x of t2 is nothing but the autocorrelation, that is Rxx of t1 comma t2. We are substituting instead of this value and we get this equation. So this is nothing but Sxx of omega. Now we are taking the inverse Fourier transform of Sxx of omega. So this is nothing but this from the inverse Fourier transform equation. Now Sxx of omega, which we have already seen, substituting it here and then taking e power j omega common, we get this equation. And from the properties of Fourier transforms and inverse Fourier transforms, Fourier transform of del of t is 1. So del of t is equal to inverse of Fourier inverse of 1. So we got this. Now we are having the same thing, but here instead of t we are having tau minus t2 plus t1. So this will be equal to del of tau minus t2 plus t1. So by substituting we get this equation. Now from the properties of impulse, this fill will be equal to 1 when t2 is equal to tau plus t1. So finally, since this value will be equal to 1, we get this equation. And now we are taking t1 as t, and here t2 is equal to tau plus t1. So we get this equation, that is Fourier inverse of Sxx of omega is equal to limit t tends to infinity 1 by 2t integral minus t to t Rxx of t comma t plus tau dt, which is nothing but the time average of the autocorrelation function. And if the autocorrelation function is WSS, or if it's a WSS process, then this will be equal to Rxx of tau. Sending the Fourier inverse this side, we get Sxx of omega is equal to Fourier transform of Rxx of tau, that is they form a Fourier transform pair. Thank you.